and welcome to this Red Door Analytics online course, Survival Analysis and Introduction to Concepts, Methods and Software. In this section, we will be talking about timescales. So we previously stated that time is one of the two key aspects of any survival analysis, where we always follow patients from a start time until a stop time. But note that the start and stop times do not on their own necessarily define the timescale. They rather define the follow-up time. In order to define a timescale, we also need a time origin, and by that I mean when time is equal to 0 for defining the timescale. So let's think about some examples here and try and think about where the origin of each timescale are for the following examples. So if we follow individuals from time since the end of a treatment, so these patients have a treatment, and then after the treatment, we start following these patients. Then we know that the time 0 is at the time point where they end their treatment. And then we follow them across time since the end of treatment timescale. If we instead look at calendar year as a timescale, well, then we most likely follow individuals from a more recent year. Say we follow them from year 2000, as calendar year increases, this goes on. But if you think about where is the origin of this timescale, well, it's really when year is equal to 0. We don't follow them from that timescale. We follow them from a year that's more recent because probably we don't have information from year 0. So you should be able to see here that the start time of follow-up and the origin is different in this example. And if we're looking at the age of a car, then the origin of this may be, if we're looking at since its purchase, the origin would be the time at which the car was purchased. If we think about the age of a car in terms of perhaps it's a second-hand car, then the origin would change because that may be the date of creation of the car rather than its purchase. So the origin could shift depending on the timescale for this specific example of age of a car. So there are different timescales that may be of interest in specific studies. Which timescale should you use is a good question to ask. Well, I think this really depends on the question of interest. For example, if we're interested in doing a prognosis study, we're often interested in time since the diagnosis of a disease. That's often the most important timescale to account for, and it's often the most interesting timescale to look at. But if we instead say that we're interested in looking at evaluating the incidence of a disease, it could be the attained age, or as the aging process is the most interesting timescale. For example, if we look at breast cancer, we know that the incidence of breast cancer increases across the attained age timescale. You're more likely to be diagnosed with breast cancer as you age. Another important timescale for the incidence of breast cancer could be time since childbirth for those women who have got children. So for this example, you can see that there may be two timescales that are of interest. But why is it important to think about the timescale and which to choose? Well, the rate at which an event occurs on one timescale may be different to that when calculated on a different timescale. And this is because the distribution of the person times and events can differ across different timescales. Now I'm going to show you what I mean by these two plots here. On the left-hand side of the plot, we are looking at individuals represented by different lines on the y-axis across years since breast cancer diagnosis to death. So in this example, we're again following patients from breast cancer diagnosis until their death. On the right-hand side of the plot, or the right plot, then we actually transform this to the attained age timescale. So if we focus on the left-hand side for now, we can see that all of the individuals start at time 0, which is their breast cancer diagnosis, and they're followed across this timescale. And we've seen this curve before, or this graph before in the previous section. So hopefully you're familiar with this. Then if we shift this and look at the right-hand side of the slide, onto the attained age timescale, we can see that all of these lines are exactly the same length, but they're all shifted across this different timescale. And this is because we are now following them across the same amount of time, but the timescale is shifted. So if we take the first individual, we know that we follow them from time since diagnosis for around 5 years. But here we can see that they start, actually, they have their breast cancer diagnosis around 57 years, let's say. And then we follow them for 5 years, at which point they are 62 when they exit the study. For the second individual, they are diagnosed at age 60. So when we follow them for 3 years across their time since diagnosis, then we see that on the attained age timescale, we stop following them at 63 years. And the most important thing to see here is that when we shift from these different timescales, is that the lengths of the lines are the same. So the follow-up time is exactly the same on both of the timescales. But you should very clearly be able to see that the distribution of this is very different. And if we had events also on these lines, if we had some crosses at the end of them representing when individuals died, we would also see that the distribution of the events would shift across these two different timescales. So that's everything for timescales. If you'd like to do some further reading, here are some references. I will see you in the next section.